Volume. Got it? Ah, there I go. You'd think with 4 kids I could project loud enough to even hit this big room, but apparently not. So, I've been working on Hadoop for a long time. My first patch went in before it was even Hadoop, so that was 11 years ago now. But yeah, I work a lot on, I've worked on Hadoop, Hive, and ORC. So, in the beginning, Hadoop applications all use text or sequence file. Text is slow. I talked last year about file format benchmarks, and one of the things that I talked about was how slow JSON was and how you shouldn't use it. Someone commented that they didn't know who Jason was, but he was a bad guy and they should be avoided. Sequence file, on the other hand, only supports keys and values, and it has user-defined serialization so that if you need to change the types, you're pretty much screwed. Hive added ORC file. The nice part about that was that you could say which columns to read, and it would only read and decompress the bytes it needed, but it still had user-defined serialization, and they managed to mess it up and make finding the splits very expensive. So we were still at Yahoo at that point, and we were discussing about what to do with file formats, and it's like, well, there's Protobuf, there's Thrift, but they both include the metadata scattered in with the data, so they're bigger than they should be. So we actually talked about Avro and designed what Avro should look like. But we kind of screwed up. We totally missed the fact that, hey, that row columnar thing, that's a good thing. And so with Avro, it works great. You can evolve the schema, but you still need to read the entire row, even if you only need 2 out of those 1,000 columns. So we were looking at this and like, okay, we need a new file format. Unfortunately, with the way that the ecosystem goes, of course, the Twitter guys were like, hey, we need a new file format, and that's why we have Parquet too, but that's the way it goes. So the columnar format allows you to read and decompress just the pieces you need. It's fast. You can see I included the link when you download the slides for the slides from the file benchmark last year where I compared Avro, Parquet, JSON, and ORC. It's indexed so that you can jump into the middle of the file. That's important, and you'll see part of why later. It's self-describing, right? The file has all the information you need to read the data. So all of the type information, all of the encoding is already in there. And it has a rich type system. So it supports all of Hive's types, including timestamps, and the complicated ones, right? Struct, map, list, and union. So one of the things that people often do when they are used to the traditional relational databases is that they're afraid of these complex types. Please use them, right? I've got some customers that have a 20-way join rather than use the complex types because they are used to the relational database. With the relational database, you need to do that. With Hive and ORC, you can use the complex types and you'll be much, much happier. Now, of course, one of the things that you're always very worried about is file compatibility. In particular, it automatically will detect which version of the file was written and read it back in. But you also really want forward compatibility. So we've actually been really successful so far at only making one version breaking change where it wasn't forward compatible. But to pay attention to that, we actually can write the old file format. And if we do need to change again, and actually we will because there's some encoding changes that we want to get to, you use ORC write format and pick which version you want to write to. Now that's important because if there's a new file version, you want to make sure to write the old version of your files so that the old readers can read it until the last cluster in your organization has been upgraded. So It doesn't matter right now because the only version change was between Hive 11 and Hive 12, which was a long time ago. I think all the customers are off of Hive 11, thank goodness. But at this point, we're going to change it again, so you're going to need it. Now, what does an ORC file look like? I wanted to go through a little bit of the details here so that you could understand some of the suggestions later. The file contains a list of stripes. Stripes are a set of rows, and everything you need to read those rows is in the stripe. The default is 64 MB, and the large stripe size enables efficient reads. Next, you have a footer that contains the list of stripe locations so that you can easily find where the boundaries in the file are, the type description, and the file and stripe statistics. And finally, there's the postscript. The postscript is a little bit different because it contains the compression parameters. You need that precisely because all the rest of the stuff is compressed. So if you don't have the compression parameters, you don't know how to decompress even the footer. So we put that at the bottom. We also put the file format version down there. Okay, quick one. Why is the meta information at the bottom of the file instead of a header like most file formats? Oh, come on, someone can answer. It's because HDFS is append only. And so as you're writing, you gather up the information, the meta information about the file, but you want to put it in one place and not scatter it in both the front and the back of the file. So you only have one place to read. All right, now this stripe structure has a little more to it. The indexes contain information about how the reader should jump to the start of any particular row group. Row groups default to 10,000 rows. And the min, max, and count of each of the columns within that range. Then comes the data, and finally the footer, which is the details about how the stripe is laid out. It also contains the column encoding. So for example, when you're writing with ORC, it'll automatically detect if your string column is being repeated or not. And if it's repeated, it'll use a dictionary encoding. So if you're using states or cities, it'll automatically detect that you need a dictionary there and use it. And if you, but on the other hand, if it's log data or something that doesn't repeat, it will use a direct encoding. So there's what the picture looks like. You end up with stripe following stripe, and the columns organized within each side. So if you're reading all the rows, you can read all that blue section. But if you need the indexes, it's in the green section up above. All right, now, that worked great, but we realized that a lot of our customers actually need to change the schema over time. And so we actually added support for Schema Evolution. So starting in Hive 2.1, you could append new types or new columns onto the end or have type conversions. In the upcoming 2.3, okay, I have to give a little bit of a admission here. Hive 2.2 I'm working on and is just about to get released. Hive 2.3 will come out like a month afterwards, but has a different set of patches. So Hive 2.2 will be a little more stable, and Hive 2.3 will be a little more aggressive in the features. So Hive 2.3 will have the ability to map columns by their names, so that if you insert columns into the middle of the structure, it'll figure out which ones go with which. So you can map things by name, which will be really convenient. The way you get this is the reader has a parameter that you can pass in the schema you want. So actually, if you're reading a whole set of ORC files, you just pass in the schema, and the ORC reader will do the conversions for you. The type conversions are actually really powerful. It will do all the type conversions that Hive does. Unfortunately, that list is a little complicated, but you can, most of the type conversions you'd expect to be there work and do exactly the right thing. One thing to be cautious of is that null in SQL doesn't mean the same thing as null in programming languages. Null means that there is no value here, or rather, the value is invalid. And so in the type conversions, you'll get a null if the integer value, for example, doesn't fit. So if you've converted a long into an int, but it's bigger than the size that'll fit in the 32 bits, you'll get a null value instead of the truncated value, which is actually right for what SQL expects, but it can definitely confuse programmers because we're not used to that kind of semantics. Other things to pay attention to, the name mapping requires ORC files written by Hive after 2.0. The names were always in the ORC file, but actually the binding from Hive to the ORC file didn't pass the names down right, so you got these call 1, call 2, call 3 names for the top level ones. The inner structs actually already worked. The other thing to be aware of is that some of the type conversions, in particular things like to and from decimal, can be slow because they're actually stringifying and then doing the conversion. So some of them are fast and some of them are slow. Okay, now using ORC. The easy case is from Hive. You just say stored as ORC. Actually, you can even set the default file format to be ORC, and it'll happen automatically. One thing that happens a lot less now than it used to, but Hive is really good at letting you shoot yourself in the foot. And so people think, oh, load data. I'll load data into my table, it'll just work. It doesn't work like that. Load data just copies the file into the table and says, okay, I'm done. In this case, you actually need to translate the data. And so in Hive, you do that with the insert overwrite and select from the old table. The old table can be text or whatever. Now, when you want to control the properties of the ORC files in your table, you actually have two options. You can either set the table properties, and there's an example like ORC compress. Compression in ORC defaults to zlib, but if you want to set it to none, you'd do it like that. The other option is to set your config and use the set command. Now, one of the things that happened, we originally put ORC into Hive so that that integration would be really easy and smooth. But what we realized is that we really need ORC to be accessible from outside of Hive, and in particular, things like Spark. And we needed to make it easier to grab without pulling in all of Hive. And so we created a separate project that's Apache ORC, and we've actually switched Hive to use the ORC. We were forked for a while, which was bad, but now we've got it to the place where Hive's master and the upcoming 2.3 will use the ORC project artifacts. But if you're using Java, please just go straight to the ORC project rather than using the Hive version. The group ID is org Apache ORC, and you want 1.4. One of the pieces that we add, in particular for Spark, Spark was already linking against Hive, and ORC uses the Hive classes so that it doesn't need to do translation. In particular, it uses the Hive classes for the vectorized row interface. And those classes clashed with the version of Hive that Spark wanted. So we created a no-Hive classifier, which pulls those classes into the ORC namespace so that you can link the ORC project with any version of Hive, and it won't cause any clashes. There's two levels of access. There's the core interface that gives you faster access, but uses Hive's vectorized APIs. Now, that's fast. It processes 1,000 rows at a time. Hive's vectorized is basically allocates each column as a primitive array. So if you have an int column, it actually makes a array of longs and uses one per a row and processes things 1,000 rows at a time. That's fast, but it's not very user-friendly. So ORC Core uses that interface. ORC MapReduce, works with MapReduce, but it's really row-by-row access, and it's a layer on top of ORC core that provides a more user-friendly version of that. Now, that MapReduce API actually implements writable comparable. If you tried to use the ORC struct from Hive, you would quickly find out that it doesn't actually implement writable comparable, so you can't send it through the shuffle. The new one you can, and the only restriction is that you actually need to specify the type information in the configuration for either shuffle or output. There's lots of documentation on the website, though, if you have any questions. Now, one of the interesting pieces is that we actually have created a pure C++ client. This was done for the people who had large C++ code bases, in particular Vertica has done a lot of work on this, precisely because they wanted control over memory, and pulling a JDK into their process would have blown their memory estimates and their ability to control their memory use. And so they combine it with the pure C++ HDFS client from HDFS 8707, and they actually are able to read ORC files straight out of HDFS without touching any Java at all. That HDFS 8707 is currently in a feature branch, but should be committed soon. Actually, part of the problem was that the Vertica guys were made branch committers for 8707, but not real committers, and so while it was in the dev branch, they could make commits, but they couldn't if it got committed to master, and now they're actually committers, and so it should be good. They have been using it for more than a year now, and it's pretty stable. Alibaba, on the other hand, has come in and created a C++ writer, and they've been giving it to that and doing the work of porting it into our project, and so that should be released in the next version, I expect. Really excited about that. It'll be nice to have a writer. Okay. Now, from the command line, often you get the people treat ORC files like blobs, and they really aren't. You actually can get a fair amount of information out of them. If you're using Hive, the easiest way is to use the Hive command and the ORC file dump parameter. There are a couple options, or there are a lot of options, but the two most common ones are JP, which pre-prints the metadata as JSON, and -G, which will actually print the contents of your file out as JSON. Now, in the ORC project, we've actually taken that a little further. The meta subcommand actually is the same as ORC file dump out of Hive. The data just prints it as JSON. Convert goes the other way. It'll convert from JSON into ORC. Now, if you're doing a lot of this, you should be doing it as Hive, right? Create two Hive tables, one with JSON, one as ORC, and copy between them like the command I showed you before. But if you're just doing a few files, or you're doing it for testing, this is really convenient to just say, okay, I've got these 10 JSON files that I want to convert into an ORC file so that I can test things out. And actually combined with the data, it actually gives you another capability, which is sometimes if someone wrote an old version of an ORC file and I want to upgrade it to a new version, I'll write it out as JSON and read it, convert it back into ORC, because then it'll get converted to the latest version. Now, as part of that, one of the pieces that came back is, okay, that's great, but I've got these huge pile of JSON documents, and I've got no idea what the schema is in here. Actually, one of the first cases we looked at, GitHub Archive, gives you all the log data from GitHub, and they just give you the JSON documents, and they don't give you any schema at all. So running the JSON schema tool over it will scan the documents and give you the JSON, the schema for the JSON. Okay, let's talk about optimization. The biggest thing is stripe size. It makes a huge difference in performance. But unfortunately, it's a trade-off. You control it with org stripe size or the config of hiveexec.org.default.stripesize. Okay, that's a horrible name. Org stripe size is easier. And it actually isn't really the stripe size, it's actually the amount of buffer that the writer will use to buffer up the stripe. Because it's writing it in columnar format, it needs to buffer the whole stripe in memory before it writes anything out. And so that's the size of the buffer, basically. And it's a trade-off. Larger stripes give you much more efficient reads. Smaller stripes use less memory, and they give you more granular processing of the splits. Because remember, the stripes are effectively the minimum split size that you can read. Actually, it used to be 256 megabytes, and some of the customers, in particular, the ones that were running POCs, had a lot of problems because they would write 1 million rows and it would end up as a single stripe in the ORC file, and so they would get like 2 mappers running over all their data. That didn't make our people happy, so we set the default down. Now, another thing that happens is that if you write a lot of ORC files at the same time, it will size each of the stripe sizes down automatically for you, because otherwise, if you write 1,000 ORC files at once, even 64 MB is a lot of memory. And so we didn't want the users crashing, so we automatically shrink the stripe size. Of course, the best way to fix that is to actually have your upper level system only write 1 ORC file at a time, and Hive added support for that, actually, after ORC was added. And it's called Hive Optimized Sort Dynamic Partition, because Hive's dynamic partitions look at the data, figure out which file to write to based on the data, and will spit it out. So if it doesn't sort on that key, it has to keep all the 1,000 or whatever files open at once as it writes to each one. If it sorts on it, then it can just keep one writer open at once and write to it and not crash. That's a good thing. Now, another of the things that we added was, because the stripes are actually pretty big, they don't line up exactly with the HDFS blocks. And because HDFS can completely change the set of hosts in between blocks, you can, if you've got a block that straddles, half of your data will be on one block and half of your data will be on the other block. To fix that, we actually added block padding, because we felt most people would want it. We made the default true. Although, of course, then you could end up with these horrible cases where you were wasting half a block full of space, and so we actually set a tolerance of how much you're willing to pad, and that defaults to 5% of the block size. So like I said, it happens automatically, but it basically just adds dead space at the end of the one stripe before starting the next one at the beginning of the HDFS block. Okay, now the next big piece is predicate pushdown. The ORC reader is given a search argument. Search arguments are basically predicates that are getting pushed down into the reader, and they consist of and or not combinations of predicates that consist of a column, some predicate, and a literal value. Because those we can apply based on the indexes. And so the reader will automatically skip over parts that can't contain any valid rows. ORC indexes come in at 3 levels: file level, stripe level, and the row group, which is the 10,000 rows. But the reader still needs to apply the predicate to filter out individual rows. One of the differences actually between ORC and Parquet, Parquet doesn't do any indexing below the stripe level, so they don't get that row group level. And the only level they can do predicate pushdown to is at the whole stripe level. So the row pruning, each primitive column has minimum and maximum values at each of those 3 levels, and the reader will throw things out at any of those levels. So you can skip the whole file, skip a stripe, or skip sets of 10,000 rows. One of the pieces to think about is that sorting helps a lot with min and max, right? If you've got a column sorted, actually, let me give an example. When I was at Yahoo, they wanted to partition based on property and day. That worked, but unfortunately they had to size the partitions for the US. That meant for some of the smaller markets, they ended up with these little tiny files, and nothing works well in Hadoop if you give it a little tiny file. So our recommendation back to them was, okay, don't do different partitions, sort the data on the country instead. So then you can still keep the big files, but you can throw out the data that you don't need quickly. So if you need to, if you've got a column that you need to search on all the time, definitely consider sorting it. Now, sometimes you can't sort on, you can only pick one column to really sort on. Sorting on multiple columns doesn't work that well. In particular, one of my customers needs to sort by time in their database of sales, but they sometimes need to quickly scan for particular user IDs. Now, clearly, sorting by user ID after you sorted by time doesn't work very well. And so we added Bloom filters. Bloom filters are a probabilistic bitmap of hash codes. So you're guaranteed you'll get a hit if it says it could be there, but you may get false positives. It only works down at the row level, or row group level. Basically, if you go too high, the bitmap would need to be huge and not usable. Actually, Parquet doesn't do Bloom filters precisely because of that, right? Because they don't have the row group level. They don't have any need for Bloom filters. They'd get the columns would be too big. It still requires significant space in the column, although it's a few percent of the data. You enable it by manually selecting or Bloom filter columns, and you can set the false positive rate you're willing to accept. The default is 5%. And there was a bug in ORC, so in terms of disclosure, we fixed it in master, but some of the old versions of Hive don't have this fix yet, and so you really want to make sure that your default encoding for your JVM is UTF-8. Basically, we were using the default character set for the Bloom filter hash, which is really a bad idea. It works great as long as everyone's using the same one, but if you change it, things will get false positives and false negatives. Okay, so one of the examples of Bloom filter, well, how the predicate pushdown works, there's a query from TPCDS where the table has 6,000 rows, so without any predicate pushdown, you read all 6 billion rows. With the min-max filtering, you get it down to 500,000, and with the Bloom filter, you just read 10,000 rows. And the time does similar jumps as you go down. Right, so this stuff can make a huge difference in how much you have to read and process, because you've just taken it from 6 billion down to 10,000. That can make your processing night and day. Yeah. Now, one of the other pieces that you need to be aware of, split calculation has been a feature of Hadoop since back in the beginning with MapReduce. It's always a very challenging piece because it happens before your process actually starts. So it's happening on the client before you actually get going. So in ORC, we ended up with 3 strategies. It's actually 2, but I'll talk about the third in a minute here. The BI is set for small, fast queries where you don't want to spend very much time in split calculation. And it just reads the blocks and splits blindly, and it deals with it after that. On the other hand, there's ETL, which is for large queries. That one, it actually reads the file footers and applies the pushdown predicates to the stripes. That can make a huge difference. Yahoo was doing some benchmarking at one point with Spark versus Hive. And most of the queries were coming in pretty close, because it was after we did TES. But when they got to one query, they're like, what's going on? Why is this running so fast under Hive? Is it broken? And actually, it was exactly this, right? because of the push-down predicates, they were able to run one map reading 10,000 rows instead of searching it was actually the query on the previous page, reading the 6 billion rows. And even though Spark had it in memory, reading 6 billion rows, even from memory, takes a long time. And so because Spark didn't have any caches, it was taking a lot longer, even on the second and third and fourth iterations. Now, if you're getting hammered on your name node because all the maps are reading the file footer, there is actually an option to include the split, or include the file footer in the split. It does cost some more in terms of the size of the split, but it does save you a lot of time, or a lot of access on the name node. Finally, there's the hybrid strategy, which if there's a lot of small, or if there's lots of small files, or there's a lot of files, it'll use the BI strategy, otherwise it'll use ETL. Okay, one of the exciting pieces is live long and process. It's of course a joke on Star Trek's Live Long and Prosper. And of course, this is an artifact of engineers naming projects, right? Our marketing department heard about LLAP and just about flipped out. But it provides a persistent service to speed up Hive. It caches both ORC and text data, and it saves the cost of yarn, container, and JVM spin-up. Even more than that, it takes and saves the JIT, of course, because the JVM stays up, and so you start much faster. If you've ever looked at performance of a JVM, for the first second, its performance pretty much sucks. First of all, it takes a second to start up, and then another second until the JIT's done a reasonable job. This avoids all of that. The cache actually uses ORC's run length encoding, but decompresses the zlib or snappy. It uses RLE because it's fast, and it saves memory so that it will be more efficient. And it'll automatically cache your hot columns and partitions. One of the side effects, actually, of LLAP is that you can actually use it to control access to rows and rows and views, columns and rows, based on Hive security, and so you can get a consistent security policy between Hive and Spark. Okay. Let's see. So what fun stuff are we doing? One of the pieces that we have done is added ACID transactions to Hive. For a long time, the JIRA where we were proposing this was the most watched JIRA in the whole Hadoop space. Mostly because people were always told, hey, you can't do ACID in the Hive or in any Hadoop system, and we actually have done it. The current implementation uses Delta files in HDFS to store the changes for each partition. Those Delta files store insert, update, and delete operations, and we use them to support the standard SQL insert and delete commands. Unfortunately, update operations don't allow the predicate pushdown on the Delta files. That created some significant hurdles for us and created slowdowns that we didn't want. In particular, right now the ACID transactions are optional on Hive tables, and we want to make them mandatory. So in the upcoming Hive 2.3, we added a new ACID layout that changes all the updates to an insert and a delete, because with that strategy, then you can actually do the predicate pushdown on the Delta files. We also added a SQL merge command that's coming in Hive 2.2. Finally, there's one more piece that I wanted to talk about. There's ORC 14, which is column encryption. A lot of people have the case where they need to mix PII or credit card information in with their other data. And it's a pain in the tail right now to put it into the same HDFS file, because HDFS, of course, has no permissions in the middle. So what we're doing is actually adding the column encryption, where because it's columnar, you can actually encrypt the whole column together. You're going to be able to specify which key you want to use for which columns. And it'll be able to use the key management server from Ranger or Hadoop. It, of course, includes both the data and the index. One of the use cases that companies often have is that they need to anonymize data after 90 days. This can help do that. If you roll the keys every day, then by just forgetting the old keys, then you can effectively not have access to the data after those 90 days. Now, of course, one of the questions that immediately comes up when you start doing encryption is like, okay, well, what do the people without the key see? The easiest one is, of course, to get null, but there are other answers. And so actually, ORC 14 is going to give you an option. The easy one is to pick nullify, which will produce nulls for every value. But you can also do a redact where the characters are replaced by X's, or you can configure what it is. Or you can get a checksum so that you can do joins, right? You can also drop or keep the first 4 or keep the last 4. You can configure how much you want to keep and then redact the rest. So this is new work, but it'll be really exciting because it'll let you do a bunch of use cases that you can't currently do. Okay, that's my presentation. Any questions? Yes.
My ORC table is an external table,
Mm-hmm.
and it has gone through several versions of Schema Evolution. If for some reason someone dropped a piece and all the partitions are gone, is there a way to create all the partitions?
So the information is actually in the file. Oh, so the question is, he's gone through several iterations of Schema Evolution, and but someone dropped the table, and he needs to get it back. First of all, you should have backups of your database. Shame on you. But fundamentally, the information's in each of the files, and so you can actually use the ORC file dump to take a sample file out of each partition and recreate the schema for the partition.
But there's no easy way to just use the latest partition.
Well, sure, you could just grab the latest partition and use that for the whole table. Yeah.
Can I go for multiple columns and
Yes, it's a list of columns. So the question is, can you use multiple columns for Bloom filters? And yeah, you would just list off the names of the columns that you want, and then it would do Bloom filters for the ones you list.
And what is the optimal stripe size that I can use? I know the default is like 10,000.
Oh, the row group size, yeah, it's 10,000. That 10,000 seems to be a good trade-off, actually. Yes?
Do you consider about column family feature?
I assume the main feature you want out of that is to put it into an external file. Oh, sorry, he's asking about column family. Most of the features of column family you'd get just by making a struct with the data there. But if you really wanted to write them into a side file, we can't do that right now. In HDFS, it would be pretty damaging to your performance to have to read a side file all the time because you can't control the locality of that side file. Yeah?
Z standard.
I'd love to put that in. Right now, Facebook hasn't released a Java client to do it. Once there's a Java client, in particular, we've actually put some other compression formats into the ORC project standalone based on the Presto airlift compressors. So once they put it into airlift, it would be absolutely trivial to add. I mean, like an hour. Yes?
What is the best strategy for storing streaming data in ORC without using the columnar optimization?
Well, you can't really turn off the columnar optimization. You'd probably want to use no compression and use a relatively small stripe size. There is a command on the Java side, or actually Hive Streaming will use it too, which flushes it and puts a temporary footer in. So that's the primary thing that you would need to do. And then other clients can come in and read up to that footer. So look at the Hive streaming stuff. How to do it's in there. Yes? Oh, okay, last question.
When we use struct or array on a column, can we still use analyze table?
Yes, you can use analyze table. Some of Hive's a little more awkward with the struct or array. Okay. Well, thank you very much.